Hi friends, in the last lecture we discussed the operation of full wave rectifiers, learned how a center tapped full wave rectifier works, discussed the effect of the turns ratio on the rectifier output. In the case of voltage regulators, we analyzed power supply filters and regulators, described the operation of a capacitor input filter, defined ripple voltage and calculated the output voltage of a filtered full wave rectifier. Today we shall talk about another important analog circuit, that is the voltage regulator and clamper. While filters can reduce the ripple from power supplies to a low value, the most effective approach is a combination of a capacitor input filter used with a voltage regulator. A voltage regulator is connected to the output of a filtered rectifier and maintains a constant output voltage or current despite changes in the input, the load current or the temperature. The capacitor input filter reduces the input ripple to the regulator to an acceptable level. The combination of a large capacitor and a voltage regulator helps produce an excellent power supply. Most regulators are integrated circuits and have three terminals: an input terminal, an output terminal and a reference or adjust terminal. The input to the regulator is first filtered with a capacitor to reduce the ripple to less than 10%. The regulator reduces the ripple to a negligible amount. In addition, most regulators have an internal voltage reference, short circuit protection and thermal shutdown circuitry. They are available in a variety of voltages including positive and negative outputs and can be designed for variable outputs with a minimum of external components. Typically, voltage regulators can furnish a constant output of 1 or more amps of current with high ripple rejection. Three terminal regulators designed for fixed output voltages require only external capacitors to complete the regulation portion of the power supply as shown in the figure. Filtering is accomplished by a large value capacitor between the input voltage and ground. An output capacitor typically of 0.1 microfarad to 1 microfarad is connected from the output to ground to improve the transient response. An example of a basic fixed power supply circuit with a 5 volt voltage regulator is shown here. It comprises of a transformer, a bridge rectifier and the voltage regulator. Percentage regulation. The regulation expressed as a percentage is a figure of the merit used to specify the performance of a voltage regulator. It can be in terms of input line regulation or load regulation. The line regulation specifies how much change occurs in the output voltage for a given change in the input voltage. It is typically defined as a ratio of a change in output voltage for a corresponding change in the input voltage expressed as a percentage given by this equation. Load regulation. The load regulation specifies how much change occurs in the output voltage over a certain range of load current values, usually from minimum current, that is no load, to maximum current, that is full load. It is normally expressed as a percentage and can be calculated with the following formula, where VNL is the output voltage with no load and VFL is the output voltage with full load. Here we shall discuss the concept with this example. A certain 7805 regulator has a measured no load output voltage of 5.18 volts and a full load output of 5.15 volt. If we are to calculate the load regulation expressed as a percentage, we would use this formula. By substituting the values given in the example, we get the result like this. Diode limiters. There are a variety of diode networks called clippers that have the ability to clip off a portion of the input signal without distorting the remaining part of the alternating waveform. The half wave rectifier discussed previously is an example of the simplest form of diode clipper. Depending on the orientation of the diode, the positive or negative region of the input signal is clipped off. There are two general categories of clippers, series and parallel. The series configuration is defined as one where the diode is in series with the load, while the parallel variety has the diode in a branch parallel to the load. Figure here shows a diode positive limiter, also called clipper, that limits or clips the positive part of the input voltage. As the input voltage goes positive, the diode becomes forward biased and conducts current. Point A is limited to plus 0.7 volt when the input voltage exceeds this value. During the limiting of the positive alternation, the diode is forward biased in the positive alternation above 0.7 volt and reverse biased during the negative alternation. When the input voltage goes back below 0.7 volt, the diode is reverse biased and appears as an open. The output voltage looks like the negative part of the input voltage, but with a magnitude determined by the voltage divider formed by R1 and the load resistor RL, as given by this equation. If R1 is small compared to RL, then V out is almost equal to V in. If the diode is turned around as in this figure, the negative part of the input voltage is clipped off. When the diode is forward biased during the negative part of the input voltage, point A is held at minus 0.7 volt by the diode drop. When the input voltage goes above minus 0.7 volt, the diode is no longer forward biased and a voltage appears across RL proportional to the input voltage. Here we shall discuss a practical example. As shown in the figure, we have a limiter circuit with V in equal to 10 volts. We are to find out the output waveform and the V peak out. In the figure shown, the diode is forward biased and conducts when the input voltage goes below minus 0.7 volt. So, for the negative limiter, determine the peak output voltage RL by the following equation. Substituting the values, we get the result as shown here. The oscilloscope will display an output waveform as shown in the figure. Biased limiters. The level to which an AC voltage is limited can be adjusted by adding a bias voltage V bias in series with the diode as shown in the figure. The voltage at point A must equal V bias plus 0.7 volt before the diode will become forward biased and conducts. Once the diode begins to conduct, the voltage at point A is limited to V bias plus 0.7 volt, so that all input voltage above this level is clipped off. To limit a voltage to a specified negative level, the diode and bias voltage must be connected as in figure here. In this case, the voltage at point A must go below minus V bias minus 0.7 volt to forward bias the diode and initiate limiting action. By turning the diode around, the positive limiter can be modified to limit the output voltage to the portion of the input voltage waveform above V bias minus 0.7 volt as shown by the output waveform. Similarly, the negative limiter can be modified to limit the output voltage to the portion of the input voltage waveform below minus V bias plus 0.7 volt as shown by the output waveform in figure. For the practical example, we will find out the output waveform of this combination of positive and a negative limiter. Here we are given an input voltage of 10 volt and we are to see the output voltage waveform on an oscilloscope. As shown here, when the voltage at point A reaches plus 5.7 volt, diode D1 conducts and limits the waveform to plus 5.7 volt. Diode D2 does not conduct until the voltage reaches minus 5.7 volt. Therefore, positive voltages above plus 5.7 volt and negative voltages below minus 5.7 volt are clipped off. The resulting output voltage waveform is shown in figure. The bias voltage sources that have been used to illustrate the basic operation of diode limiters can be replaced by a resistive voltage divider that derives the desired bias voltage from the DC supply voltage as shown in the figure. The bias voltage is set by the resistor values according to the voltage divider formula. A positively biased limiter is shown in figure A. A negatively biased limiter is shown in part B, and a variable positive bias circuit using a potentiometer voltage divider is shown in part C. The bias resistors must be small compared to R1 so that the forward current through the diode will not affect the bias voltage. A limiter application. Many circuits have certain restrictions on the input level to avoid damaging the circuit. For example, almost all digital circuits should not have an input level that exceeds the power supply voltage. An input of a few volts more than this could damage the circuit. To prevent the input from exceeding a specific level, you may see a diode limiter across the input signal path in many digital circuits. Diode clampers. A clamper adds a DC level to an AC voltage. Clampers are sometimes known as DC restorers. Figure shows a diode clamper that inserts a positive DC level in the output waveform. The operation of this circuit can be seen by considering the first negative half cycle of the input voltage. When the input voltage initially goes negative, the diode is forward biased, allowing the capacitor to charge to near the peak of the input. Just after the negative peak, the diode is reverse biased. This is because the cathode is held near V peak in minus 0.7 volt by the charge on the capacitor. The capacitor can only discharge through the high resistance of RL. So, from the peak of one negative half cycle to the next, the capacitor discharges very little. The amount that is discharged of course depends on the value of RL. If the capacitor discharges during the period of the input wave, clamping action is effected. If the RC time constant is 100 times the period, the clamping action is excellent. An RC time constant of 10 times the period will have a small amount of distortion at the ground level due to the charging current. The net effect of the clamping action is that the capacitor retains a charge approximately equal to the peak value of the input less the diode drop. The capacitor voltage acts essentially as a battery in the series with the input voltage. The DC voltage of the capacitor adds to the input voltage by superimposition as shown in part B of figure. If the diode is turned around, a negative DC voltage is added to the input voltage to produce the output voltage as shown in this figure. Now, we shall discuss a practical example. As shown in this figure, we have a clamping circuit with a large enough RC time constant to prevent the discharge of capacitor. With the given parameters of the circuit, we are to calculate the output voltage across RL. Ideally, a negative DC value equal to the input peak less the diode drop is inserted by the clamping circuit. Here V peak in is equal to 24 volts. Substituting this value in the equation, we get VDC as minus 23.3 volts. Actually, the capacitor will discharge slightly between peaks, and as a result, the output voltage will have an average value of slightly less than that calculated above. The output waveform goes to approximately plus 0.7 volt as shown in figure. A voltage doubler is a voltage multiplier with a multiplication factor of 2. A half wave voltage doubler is shown in the figure here. During the positive half cycle of the secondary voltage, diode D1 is forward biased and D2 is reverse biased. Capacitor C1 is charged to the peak of the secondary voltage less the diode drop with the polarity shown in part A. During the negative half cycle, diode D2 is forward biased and D1 is reverse biased as shown in part B. Since C1 can't discharge, the peak voltage on C1 adds to the secondary voltage to charge C2 to approximately 2 V peak. Applying Kirchhoff's law around the loop as shown in part B, the voltage across C2 is Vc1 minus Vc2 plus Vp is equal to 0. Vc2 is equal to V peak plus Vc1. Neglecting the diode drop of D2, Vc1 is equal to V peak. Therefore, Vc2 is equal to V peak plus V peak, that is equivalent to 2 V peak. Under a no load condition, C2 remains charged to approximately 2 V peak. If a load resistance is connected across the output, C2 discharges slightly through the load on the next positive half cycle and is again recharged to 2 V peak on the following negative half cycle. The resulting output is a half wave capacitor filtered voltage. The peak inverse voltage across each diode is 2 V peak. If the diode were reversed, the output voltage across C2 would have the opposite polarity. Full wave voltage doubler. A full wave doubler is shown in figure. When the secondary voltage is positive, D1 is forward biased and C1 charges to approximately V peak as shown in part A. During the negative half cycle, D2 is forward biased and C2 charges to approximately V peak as shown in part B. The output voltage 2 V peak is taken across the two capacitors in series. Voltage tripler. The addition of another diode capacitor section to the half wave voltage doubler creates a voltage tripler as shown in figure. On the positive half cycle of the secondary voltage, C1 charges to V peak through D1. During the negative half cycle, C2 charges to twice V peak through D2. As described for the doubler, during the next positive half cycle, C3 charges to 2 V peak through D3. The tripler output is taken across C1 and C3 as shown in figure. So friends, in this lecture, we discussed voltage regulators and talked about their line and load regulation, explained and analyzed the operation of diode limiters and clampers, discussed biased limiters, voltage divider bias, and lastly talked about operation of a diode clamper. So that is it for today. See you in the next lecture. Thank you very much.